let's hit record so that we have a record of what we do now. Okay. Do you guys have the problem numbers for me? Or do I have to do that too? Grrr.
All right, one sec, I'll pop them up. The problem numbers are, it's chapter 5.
Yep.
44, 53, 54, 55, and 57.
All right. I'm ready to roll. Let's start with chapter 5, number 44. What's the question ask? Or what's the title?
All right, 44 is Atomic Terminology Practice 2. A is what are the atomic number and atomic mass number of a fluorine atom with 9 protons and 10 neutrons? If we could add a proton to the fluorine nucleus, would the result be fluorine? Would the result still be fluorine? What if we added a neutron to the fluorine nucleus? Explain.
Okay, so what if we add a proton? What if we add a neutron? Are these all the questions, or did I miss any? They ask for the atomic number, they ask for the mass number, they ask what happens if we add a proton, they ask what happens if we add a neutron. Anything else that I missed, Dennis?
All right. Mass number, proton, neutron, and then add the neutron to see, and then added the neutron to the fluorine nucleus. Yeah.
Okay, so it sounds like 4 questions in one. Let's start easy. What's the atomic number?
Wouldn't it be 9?
That's right. It's just the number of protons. The mass number?
$19.
That's good. You add the 9 and its protons and the 10 neutrons. If we add a proton, does we add its, huh? I apologize, guys. What? Talk to me. If I add a proton, does fluorine stay fluorine?
Wouldn't it be no?
Right. That's correct, Megan. Why?
Because then the atomic number and then the mass number would change and it would be another element.
That's right. Any wild guess as to what it would be? 10 protons? It's neon.
No idea.
No. If we add a proton, the atom would change to neon. And if we add a neutron, is that still fluorine?
No.
Yes. The atomic number defines the atom. This is what we learned last time. What does the mass number define?
Isn't it the number of protons and neutrons?
that's what the mass number is, but it represents something about the atom. But a different, can you see what I'm writing? Yes, this would still be a fluorine atom, but now a different, what's our $10 word there? It's not that it's a different atom, it's that it's a different, I thought I was having a late start today. We got to turn on our brains. Look in that notebook. What do you see? What does the mass number define?
Would it be isotope?
Thank you. That's right. This is a new isotope, and the isotope would be called fluorine 20. I think it's FL for fluorine. Correct me if I'm wrong. Let's get Mr. Internet up here. Images. Where's the one that I like? Tools, size, large. I really should save this damn file before the internet takes it away from me. There's one that I don't know, I like the graphic design on it. It's the one I always show you guys. Where is it? I need to save it because it's, Ooh. It's kind of like this one. This one. This is the best one. Why don't I thought I had saved this many a time. Let's just save that image while we can. There we go. All right. Why did I call this up? Oh, sorry. Fluorine is just F, not FL. Shows what I know. Not much of a chemist. Class, bear with me for just 1 second. I cannot minimize. Okay, fine. I need to move my old Zoom files out before I record any more of this lecture. I always forget to do this. My desktop has limited space, and I live in fear of this recording not working, because then any student who might miss it would truly miss it. So I'm going to just move these files to December 20, paste. Yeah, okay. Otherwise, this recording will crash. All right, that takes care of part A. Dennis, are you ready to read us part B?
Yeah.
Hold on, let me get the Windex here. This board's getting icky. I think it's time to open up my black marker spot. Let me try this guy. It's kind of bad. That's kind of spotty, but we'll give it a shot. Okay, Dennis, let her rip.
All right. 1 sec. So it is 44B. All right. So, the most common isotope of gold has an atomic number 79 and an atomic mass of 197. How many protons and neutrons does the gold nucleus contain? If the isotope is electrically neutral, how many electrons does it have? If it is triply ionized, how many electrons does it have? Am I silenced here?
No, I can hear you.
All right. Yeah, that was the whole question. Yeah. All right.
Is triply with an E-Y or just a Y?
Yeah, let me check that. Just TRIPLY.
Okay, I got it right then. Okay. Dennis, can you answer any of these questions? The number of protons should be pretty easy.
All right, so yeah, let me I can get it off the information on the board right here, right?
Yeah, somewhere between the atomic number and the mass number, that we should know the number of protons.
It's the atomic number is 79. All right.
Just excuse me. Look at your notes. What does the atomic number mean? You gotta we gotta keep practicing till we remember this stuff.
Yep. It's right in here.
Okay.
Give me like 2 seconds. Where did I put that?
So how about that exam, huh? That was a good time.
It was great. It's fantastic.
The first half of the exam was super easy, and the last half I was like,
You were dying. Yeah, the math stuff can get crunchy. But believe it or not, usually I detect an increase in skill from students after going through it. So thank God we only have to do one of those, right? No more stress. The rest of the class is just fun.
woo!
Woo. Okay, but I still need to know what the atomic number
Yeah, can you
means.
give me just like a quick hint, like, and I'll be able to figure it out because my notes are kind of like long here. Like,
Protons are 79 because that's the atomic number.
Yeah, the hint is kind of like the answer. The atomic number means the number of protons. So
All
it's
right,
just
yeah,
79.
okay.
Sorry to drag that out there. Okay, Tess, since you're with it, how about the number of neutrons? What do we do there?
I only knew that.
Anyone?
Would that just be half of the mass?
No, not half.
You would just do the 197 and subtract 79 protons, and then you'll get the number of neutrons.
Right, because this number is the number of protons plus the number of neutrons. And we know the number of protons is 79, right? So what do you get if you do 197 minus 79?
118.
All right. How about if it's neutral? How many electrons? What does a neutral atom mean? I thought these were pretty elementary questions. Neutral.
Same amount of protons and electrons, like it has a neutral charge.
If they are equal to each other, then it's neutral. There's no net charge. So how many electrons do we have? No tricks. I just gave you the hint, right? You know, protons and electrons.
79.
Pardon?
79.
Exactly. They've got to be balanced.
Bless
What
you.
is triply ionized? This is going to be like pulling teeth today if we move this slow.
Wouldn't you have to remove or add an electron?
Let's say they're removed. Usually you strip them off. So triply ionized, how many electrons are left?
Would you just remove 3, or would that be?
Yeah, that's what triply means, 3 times.
Oh, then that's 76.
Yeah. I mean, I thought that was easy, but I don't know. I don't know what's easy for you guys.
Simple math always seems to be the hardest.
Yeah. All right. Boy, it's a good thing we're reviewing atoms in this class, I'll say that. Everyone got that? I'm about to erase. Dennis? Part C. Did I lose Dennis? Where is he?
No, I'm unmuting and bringing up the other
Oh,
screen.
okay.
All right, so 44C. Uranium has an atomic number of 92. Its most common isotope is 238U, but the form used in nuclear bombs and nuclear power plants is 235U. How many neutrons are in each of these 2 isotopes of uranium?
This is how they used to do it back in the day. They'd write the symbol for uranium, U. You'd put the mass number up here, U-238, and you'd put the atomic number down there. And sorry, what did they ask? What they ask again?
So uranium has an atomic number of 92. Its most common isotope is 238U. The form used in nuclear bombs and nuclear power plants is 235U. How many neutrons are in each of these 2 isotopes of uranium?
Okay, let's start with U-238. How many neutrons? You're basically doing exactly what you did in the last problem.
146.
Huh?
146?
How'd you get that? I want to make sure everyone knows that.
I just subtracted 138 from 92.
238 minus 92, you mean?
Yeah, sorry.
Fudge. Okay, U-235.
143.
Well, gee whiz, that was fun. Okay.
Oh, hold on. All right.
All right, let's try 53. Amber, you want to read that one for me?
I have to pull it up.
We should always have the questions with us when we're doing this. You should always read, you owe it to yourself to read the question at least.
Kilowatt.
getting my stool out because you guys are slow today.
Electric bill.
Oh,
Your
sorry.
elec-
Electric bill?
Yes.
Okay, hit me.
Your electric utility bill probably shows your energy use for the month in units of kilowatt hours. A kilowatt hour is defined as the energy used in 1 hour at a rate of 1 kilowatt, 1,000 watts. That is 1 kilowatt hour equals 1 kilowatt times 1 hour. Use this fact to convert 1 kilowatt hour into joules. If your bill says you used 900 kilowatt hours, how much energy did you use in joules?
So there's two problems here. First, we're going to convert 1 kilowatt hour into joules. Then we will convert 900 kilowatt hours into joules. We got two problems. Let's begin with 1 kilowatt hour. Did we do power? I don't think we did power last time, did we? Do you have any notes on power?
We did like potential energy, and there's some about the calories and then 1 joule.
Okay, so here's how this works. Watts are units of something called power. Power in physics is energy divided by time. It's a rate of energy flow. Power is not the same thing as energy. It's a flow of energy. And it uses units called watts. 1 watt is equal to 1 joule per second. That's crucial for doing this problem. That means if we multiply kilowatts times a unit of time, hours, that's ultimately an energy, which can be expressed in joules. We are going to attempt to convert 1 kilowatt hour into joules. We will do so with our favorite technique, the technique which is called, class,
Shit. I know what to do. I just don't remember the name.
remember the name.
Dimensional analysis.
Dimensional analysis, Megan. Very good. Okay, Brandon, you know what to do, so start us off.
We just put 1 kilowatt.
No, you don't put 1 kilowatt. Kilowatt hours are a different unit than kilowatts. Do you feel me?
Oh, yeah. Okay, maybe I don't know what to do. I lied.
Thought you were tough, huh? Why don't you start with 1 kilowatt hour and show me how tough you are? Now what? You proceed exactly the same.
So you do times a division bar.
Okay?
And then
Kilowatt hours are a unit, but you can treat them separately. So let's treat each one separately.
so would it be 1 kilowatt on the bottom?
Don't give me any numbers.
Okay.
You can put
Oh,
kilowatts on the bottom.
yeah.
What are you
And
going to
then-
put on top?
Joules, right?
We don't have a conversion from kilowatts into joules. In fact, that doesn't make any fucking sense because kilowatts are a unit of power and joules are a unit of energy. You might as well just convert bananas into kittens, like
Oh, then it would be watts at the top.
watts. Okay.
Yeah.
And what's the numbers for that conversion?
It'd be 1 kilowatt to 1,000 watts.
Okay, what are the current units that you have?
Watts and hours.
Don't say watts and hours. It's watts times hours or watt hours.
Watts times hours.
Right?
Yeah.
Watts and hours sounds like you're juggling them or something, you know, like they are multiplied by each other. One must be precise here. Okay, what do I do next?
Would you do the hours next?
Let's deal with the hours next. What should we convert them into?
We want to ultimately get to seconds eventually, right?
Yeah, because watts are expressed in joules per second. So
Yeah.
let's put a division bar. What do you want to do there?
I guess we'll do minutes on the top,
Okay.
hours on the bottom.
Okay, I'm cool with that.
It would be 60 minutes to 1 hour.
Okay, that takes care. We now have watt minutes. Now what?
And then we're going to do times or division bar. Minutes on the bottom, seconds on the top.
Yep.
And then 1 minute equals 60 seconds. Yeah, not equals.
Okay,
Sorry.
so multiply them up and tell me what I get. This is 3,600 followed by 3 more zeros, right?
Okay. $36. Oh, it's 3.6 times 10 to the 6th power.
What are the units?
Watts per second?
Not watts per second.
Oh, then it would be joules per second.
No. No, listen, dude. Watts per second is this. That is not the units you have. Look across your thing. Seconds are not on the bottom.
Oh, so it would be seconds on the top?
So what are the units?
It'd just be seconds.
No, what about the watts?
I don't know why I'm not following right now.
Would it be watts per second?
It is not, once again, it cannot, you guys throw around the per very casually, like you can just make it up. You just want to say per because it sounds good to say per. But if you say watts per second, it means this, watts divided by seconds. Your seconds are not in the denominator. They are in the top. How do we say this? How do we write this?
Is it watts times seconds?
It's watts times seconds, or watt seconds. No per. But I was supposed to get an answer in joules.
Wouldn't it just be what? 3.6 million joules?
That's right. Because a watt is a joule per second.
Yeah. Okay. I'm just making sure.
Which is 3 points. I just wanted to see if you guys could see that. Right? So 1 kilowatt hour is 3.6 million joules. But it was up to you to figure that out, you know? That's half of our, I'm sorry?
I was just saying, don't erase yet. I got to catch up with.
Sure. Because you were talking.
Yeah.
We've completed this problem. We now have to tackle the next problem.
For the next problem, would you just be able to times it by 900?
That's exactly the idea, because we've kind of come up with a new conversion factor. We now know the direct conversion factor from 1 kilowatt hours to joules. So we might as well employ that here, right? So that I was hoping you'd say that, Brandon, or I was hoping somebody would say that. So we start with 900 kilowatt hours, and now we're going to convert directly from kilowatt hours into joules because we now have a conversion factor. So 1 kilowatt hour is 900 joules. Kilowatt hours cancel. We're now treating both of them together. And I'll take that answer whenever you're ready.
Oh, shit. Oh, sorry. 1 second. $800 or what? How do I say that? Oh, 810,000.
No way. Oh, sorry. I made a mistake here, guys. Look, I did something really, really dumb.
You put 900 in the joules place.
Right. What was I supposed to put there?
3.6 times 10 to the 6.
Yeah.
There's me following it. That's fine.
Yeah.
All right. 900. 6. 3. Uh, 3 times 10 to the 9th.
Okay. How about 2 sig figs?
3.2 times 10 to the 8th.
Wait, why did your power change?
Oh, you're right. No, you're right. Yeah, 3.2 times 10 to the 9th.
Joules.
Joules. I see, because I did the decimal thing. That was dumb.
That's all right. That's all right. Y'all's is learning, I think.
At least joules to watts is just 1 to 1, or joules second is 1 to 1. I guess that makes it a little bit easier, right?
Yeah. Yeah, watt is a joule per second.
Yeah.
We'll talk more about power in today's lecture.
I forgot, is it volts or watts that will kill you? I think it's volts, right?
Well, technically it's the current that kills you, but there's a relationship between current and power and voltage. You have to take an electricity and magnetism class to appreciate all of it, but it's not super, super complicated. Volts do not measure power. Volts measure something called electrical potential. You can think of it as the field that it's the ability of some charges to push another charge.
It's the
The oomph, kind of, yeah. You know how like you can feel the magnetic field push a magnet? That's kind of like magnetic potential. But there's an equivalent of electric potential. It's the ability of a wall of charge to accelerate a charged particle. It's not exactly the same thing as power, but they are related by a formula, which I don't need to explain to you because it's just going to be confusing. It's power equals the square of the current times the resistance. Electricity and magnetism is a very interesting course. You kind of learn how all these cool machines around you work. I strongly encourage learning about it. I'm going to erase now. How about 54? Let me just say that 54 probably has to do with light. What's the title of it?
radio station.
Okay, so today we're going to be learning about different types of light. And unfortunately, we haven't quite got to these 3 formulas, but light is an electromagnetic wave. Let's draw a picture of this. So here's your radio tower. We can put some support structures there if you want. And it's got a flashing light. And we're going to generate a radio wave, which is basically a ray of light. And light is an electromagnetic wave. We're going to talk about its properties today. One of the properties that waves have is the distance from crest to crest of the wave is called the wavelength. And wavelength gets kind of a funny symbol here. Wavelength gets the Greek letter lambda as its variable. Lambda looks like an X that turns into a slide. It's an X missing an arm, okay? It also has a property called frequency. We're going to use a curvy F. And it has a third property. Light is a pure form of energy, which we like to use capital E for. And these three quantities are related to each other by a couple of famous formulas that you're going to be using in this problem. The first formula, I sometimes call it Formula 1, is that the speed of light is the wavelength times the frequency, where the letter C represents the speed of light in a vacuum. It's a constant value of 3 times 10 to the 8 meters per second. The energy of a photon is given by the famous formula E equals H times F. Here, H is another wacky constant of nature, 7 times 10 to the minus 34 joules times seconds. And I'll introduce this in class today. This is called Planck's constant. You don't need to worry too much about what that means right now. It's just a number. The units of wavelength are usually meters. I'll put this in a different color here. So wavelength is usually measured in meters. Frequency is usually measured in hertz, which is the same thing as 1/seconds. And energy, of course, is measured in joules. Okay, I think now that I've written all that down, I'm ready to hear the problem, Brandon.
Okay. Radio station. What is the wavelength of a radio photon from an AM radio station that broadcasts at 1,120 kilohertz? What is its energy?
Okay, let me explain what's going on here. We've been given the frequency of the radio wave, 1120 kilohertz. Given the frequency, we're now asked to find both the wavelength and the energy. The first issue is that frequencies are usually measured in hertz, not kilohertz. So we have to convert kilohertz to hertz. How are we going to do that?
Dimensional analysis.
Hell yeah. With our number, let's start with 1120 kilohertz.
And then it would be it'd be kilohertz on the bottom.
Yep.
Hertz on the top.
Yep.
1,000 hertz. Yep.
Yeah, you know that a kilo is 1,000, right?
Yep.
So can you do that in your head, Brandon? I'll get you started. 1.12 times 10.
To the it's not 4, is it? No.
No, you've got to count this one, this one, this one, this one, this one, this one.
Oh, 6.
Right, hertz. And 1.12 million hertz is the same thing as 1.12 million. We sometimes say cycles per second, but it's written as 1/seconds. That's what a hertz is. It's a cycle per second. It's a number of these. So this is our frequency expressed in MKS units. Now we can use one of our equations to solve for wavelength. Do you want equation 1 or equation 2?
Would it be equation 1?
Yeah.
Because,
Change that to solve for wavelength.
oh, sorry, what was that you cut out?
We would need to rearrange this to solve for the wavelength. Can you do that?
Um,
So we
I can
currently
try.
have speed of light is wavelength times frequency. I have to solve for this guy.
Wouldn't you have to have frequency on the other side somehow? Or
Yeah, so you drop it down, what do you get?
would it be frequency divided by? No.
No. Look, if you cross the equal sign, you have to flip the equation, right?
Yeah.
So if you push lambda to the other side, you have C over lambda equals frequency.
Oh, so it'd be frequency over, no, would it be C over frequency equals lambda?
That's right. If you push the frequency down here, you have C divided by frequency equals lambda, right?
Yeah.
Which is the same thing as wavelength is the speed of light over the frequency. They're symmetrical, right?
Yes.
Okay.
Cool. So where's my calculator that I threw on the ground?
Yes. So we have wavelength is the speed of light divided by the frequency. Speed of light is 3 times 10 to the 8 meters per second. That's always the same. The frequency is 1.12 million cycles per second.
Three sig figs, right?
Yeah, I guess you could keep 3.
Um,
The speed of light is good to 3 sig figs.
would it be, I got 267.
Okay. What's the number after 7?
Oh, so I guess it'd be 268.
Yeah, we don't stop rounding, right?
Yeah.
What are
But
the
we just-
units?
That would be wavelength? Oh, no, wait, hold on. Sorry. Second. It'd just be meters, right?
Yeah, meters. Wavelength is the quantity. Meters are the units.
Oh,
Meters are to wavelength as dollars are to money. You measure money in dollars. You measure wavelength in meters. But dollars does not equal money. That's a weird thing to say. Right?
how many monies do you have?
Yeah. Well, or it's like saying, how much dollars do you have? You can say that, but it's weird.
Doesn't sound right.
People will understand you, but it's weird.
Cool. Is that it for that question?
Nope, that's the wavelength. We got to do the energy now. What are we going to do about the energy?
Oh, we would use the second formula, right?
Yeah. Can I erase this a little bit here?
Yes. Well,
All right. Brandon's saying yes, so I say yes. Okay, so the second formula is that the energy of the photon is Planck's constant times the frequency. Planck's constant is 7 times 10 to the negative 34 joules times seconds. What am I going to multiply that by?
1.12 times 10 to the 6th hertz.
Cycles per second.
Or cycles per second.
I'm running out of board space here.
I got 7.84 times 10 to the negative 28th power.
Yeah, let's just do 7.8 times 10 to the minus 28. What are our units?
That'd be joules, right?
Yeah. Sorry, I wrote that a bit sloppy-ish.
Is it even, because I was thinking about this, is it even possible to do any of these equations without a calculator?
Yep.
Or would it just take you forever?
Well, what's 7 times 1? That's 7.
Yeah.
And what about our times tables? What's 7 times 12? 84. That gives you 7.84. Negative 34 plus 6 is positive 28. Oh, I'm sorry, positive 20. Sorry, negative 29. No, negative 28. You can do it without a calculator, dude. You just got to know your times tables.
Yeah. Okay.
You know what I'm saying?
Yeah.
You could always get a rough answer anyways.
Cool.
Okay. I'm erasing.
Was that an infrared joke?
Say that?
You said IR. Was that an infrared joke?
I meant to say I'm erasing. Did it sound like IR?
Yeah, I thought you said IR racing.
Oh. No, I wish I was that witty right now, but I think I'm feeling under the weather. That was 53, so next is 54. 54 is more on those those two equations that I taught you.
We just did 54.
Oh, we did? Yeah, hell if we did. So now, wow, we're moving right along then. Now we're on 55.
So want me to read it?
Yeah, sure. What's the title?
UV photon.
Okay.
What is the energy in joules of an ultraviolet photon with a wavelength of 120 nm?
That's nanometers. 1 nanometer is a billionth of a meter.
Jesus.
So it's 1 billionth of a meter. Nano is the prefix. They want to know the energy. What else?
What is the frequency?
We're going to need the two equations from last time. The speed of light is wavelength times the frequency. The second formula is the energy is Planck's constant times the frequency. There's also a third formula that can come in handy sometimes. If you combine Formula 1 and Formula 2, there's a formula that relates energy to wavelength. The energy of a photon is Planck's constant times the speed of light divided by the wavelength. These three formulas are our go-to formulas. We know C and we know H. So do we want to do the energy or the frequency first? What's your pleasure? Geez, guys, I feel like everyone's kind of punched out today.
Energy.
Okay, fine. Which formula do I want? 1, 2, or 3?
Is it 2?
2 relates the energy to the frequency. You don't have the frequency yet. Want to try again?
Would we be using 3?
3 relates the energy to the wavelength, and we have the wavelength, so that sounds good. You will remember that Planck's constant is 7 times 10 to the negative 34 joules times seconds. And the speed of light is 3 times 10 to the 8 meters per second. Both of those are MKS units. Nanometers is not an MKS unit.
So we have to put it in meters, right?
Yeah. I nominate Ian to do this. Ian, you've been volunteered.
All right.
Help me convert 120 nanometers into meters using dimensional analysis.
So we have 120 nanometers, and then 100, times division.
Units?
Nanometers on the bottom, and then meters on top.
Conversion?
1 on top. Right? No, sorry, on the bottom.
Oh. On top?
On top. Oh, okay. 1 times 10, negative 9 on the
Okay.
top.
Now, before you bother putting this into your calculator, what is 120 times 1 equal? No tricks. 120 times 1? Punch it into your calculator. You're going to learn something.
That's a lot of zeros.
Okay. What we have here is a failure to communicate, okay? I want to know a very simple question. The answer to a simple
120.
question. What is 120 times 1?
It's 120.
Oh, 120.
So then I can just write 120 times 10 to the negative 9 meters. That's a cute way to do it. I'm sorry, Ian, but that is not a lot of zeros. That's a lot of not zeros. That's a really, really tiny number.
Yeah.
Okay. Just so that we're straight. Now we can use equation 3, Amber. The energy of the photon will be Planck's constant, 7 times 10 to the minus 34 joules times seconds, times the speed of light, 3 times 10 to the 8 meters per second, divided by the wavelength, 120 billionths of a meter. Punch them up.
With the nanometers equation, could you do that for, like, say you got, like, let's just say 530 nanometers? Would that just be 530?
You know what's interesting?
530 times
530 nanometers happens to be the wavelength of my astronomy laser pointer here, which is a brilliant, it's not going to come out that great on your webcam, but it's a really brilliant electric green. I'm sorry, what was the question? I just got distracted by your weird choice.
I can't believe, yeah, I can't believe that. No, I was just, so you could just put anything into nanometers, like 530,
Sure.
and it would be
I could,
530
my height is 1.6 meters. I could express that in nanometers as 160 billion, wait, 1.6 billion nanometers? Yeah.
I'm going to start telling people that's my height. See what they do.
Yeah, 1.6 billion nanometers. That's pretty funny, actually.
Is it 1.75 to the negative 10? I'm sorry, negative 18.
Could you say that one more time?
Is it 1.75 to negative 18?
Something went wrong there. Can you punch that again? The power is wrong, I can tell you that. 34 plus 9, negative 34 plus 9 is negative 25. Oh shit, I'm having trouble here. Negative 25 plus 8 will bring you to, oh,
I got the same thing. 1.8 times 10 to the negative 18.
I'm sorry. I made a mistake. That must have been right. So it was 1.8 times 10 to the minus 18.
Yeah.
I am so sorry. What are the units?
Joules, right?
Yeah. Deep apologies to whoever shouted that out first. I was doing bad maths. Now let's get the frequency. Which formula should we choose for frequency? I'd say equation 1 would work.
Yo.
So the equation is frequency is the speed of light divided by the wavelength. Speed of light is 3 times 10 to the 8 meters per second. The wavelength is 120 times 10 to the minus 9 meters. Feel achy. It's not really, it's just a slight thing, but I'm paranoid that I'm getting sick. I can't tell if I am or not, but. Okay, what do you got?
2.5 times 10 to the 15th.
And the units?
Meters.
No, the meters cancel.
Oh, seconds, sorry.
Sorry, the seconds is on the bottom. Keep trying. Seconds is not the same as seconds on the bottom.
Wouldn't it be that 1 over?
Seconds.
Yeah, 1 over seconds. Yeah.
1 over seconds, which is the same thing as 2.5 times 10 to the 15 hertz.
And that would be the answer. Yeah, for frequency.
Yep.
Cool. Booyah.
Booyah. We got one more to do, and we're only at 11:27. We're doing just fine. How we doing, everyone? We all caught up? Here comes the eraser. It's gonna take a second to get the crud off the board. All right. She's squeaky clean now. Huh? Oh, yeah. Okay. Our last problem for homework today is chapter 5, number 57. Who's going to read that? Megan?
Sure. 57. How many photons? Suppose that all the energy from a 100-watt light bulb came in the form of photons with wavelength of 600 nm.
Hold on. So I'm going to draw a light bulb here. I'm using orange. It turns out that the wavelength of 600 nanometers is the same as the color orange. I'll show you that today. Okay, so it's a 100-watt bulb, right?
Yeah.
But the wavelength of the photons is 600 nanometers. This is kind of like a laser light bulb. It's a light bulb that only gives out one color of light. And the same way that my green laser only emits photons. Ooh, wow, I can totally reflect that right into the camera. Whoa. These are exactly 600 nanometers. Sorry, these are exactly 532 nanometers. The orange light bulb will be 600 nanometer photons. Okay, what's it want us to do?
A is calculate the energy of a single photon with wavelength 600 nanometers.
Okay. Which of those three equations would be the best one to calculate the energy of a 600 nanometer photon? Equation 1, 2, or 3 from your previous problem? One, 2, or 3? Pick a number.
2.
No, 2 relates the energy to the frequency. We don't
Number
have the
3.
frequency. We have the wavelength.
3.
3. Equation 3 relates the energy to the wavelength. And it says that the energy of a photon is Planck's constant times the frequency, sorry, yucky, divided by the wavelength. Planck's constant is 7 times 10 to the minus 34. The units are joules times seconds. C, the speed of light, is 3 times 10 to the 8 meters per second. And the wavelength, oh shit. Our wavelength is in nanometers. What are we going to do about that?
Make it into meters.
Okay, make it happen.
It's 600 times 10 to the negative 6 meters.
False. You should probably use dimensional analysis in that case. Here's your division bar. What is your conversion from nanometers to meters?
1 times 10 to the negative 9.
Yeah.
So wouldn't it be? What did I say? Did I not say it right?
You said 600 times 10 to the minus 7.
Oh, I meant minus 9. My bad. I
Yeah.
can't read my own handwriting.
It's 600 times 10 to the minus 9 meters. That, by the way, happens to be the same thing as 6 times 10 to the minus 7 meters. Well, whatever. We'll just do 600 times 10 to the minus 9 meters. All right? Punch them up.
3.5 times 10 to the negative 19 power.
Units?
Maybe joules.
Correct. It's an energy. Part B.
It says how many 600 nanometers photons would have been emitted each second to account for all the light from its 100-watt light bulb?
That is, they want to know how many photons per second are leaving the bulb. Now, we know the energy of the bulb. We know it's 100 watts. And that 100 watts is streaming out in all 360-degree directions. So there are light bulbs, there are photons of light that are leaving my bulb in every possible direction. And the net energy flow is 100 watts. So that means that there are 100 watts or 100 joules per second leaving the bulb. I'm trying to get photons per second. So if I do this by dimensional analysis, since I don't know the formula, what units would I have to put in to end up with photons per second?
You'd have to do joules, right?
Where?
On the bottom?
Specific. Joules would go on the bottom. What would go on the top?
Photons, right?
Yeah, photons are technically like a conceptual unit, but you can do it. If only you knew the number of photons per joule or the number of joules per photon, you'd know what to put in there. Where can I find the number of joules per photon?
In our notes, question mark?
No, it's specific to 600 nanometer light.
Oh, it'd be 600? No.
No, I need to convert from joules to photons or from photons to joules. How many joules are in a photon of 600 nanometer light?
Would it be 6?
No.
Oh, it's 3.5 times 10 to the negative 19.
Right, that's what you guys calculated earlier. You calculated the number of
Oh.
joules per one photon, right?
Yeah.
So tell me what numbers to put in here, Brandon.
It would be 3.5 times 10 to the negative 19th on the bottom.
Yep. And what goes on the top?
1, right? 1
Yeah.
photon?
Just testing you.
Okay.
Divide 100 by 3.5 times 10 to the minus 19.
Wait, did you say divide then?
Well, is 3.5 times 10 to the minus 19 on the top or the bottom?
Bottom, so, okay.
So
It
you
would
divide
be 2.9 times 10 to the 20th.
Yeah, I'm just going to round it boldly to 3 times 10 to the 20th. And my units are photons per second. That's a crazy big number of photons leaving your light bulb. That's a 3 followed by 20 zeros. There's actually a part C.
Do you want me to read it right now?
Yeah, can I erase this?
I'm good.
All right. If you're good, I'm good. What's part C say?
Based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
In other words, it's asking the question, Why can't I see one single photon? Does anyone want to guess the answer to that question?
Because a photon is incredibly, no, it's big.
I'm sorry, what were you saying?
Is it because a photon's incredibly small?
Well, I agree. So one answer is too small. I agree with you that 600 nanometers is a small wavelength, but it turns out, Brandon, that all orange light has a wavelength of 600 nanometers. So if 600 nanometers was too small for the eye to see, you wouldn't be able to see the color orange. So that's clearly not true. So too small is not the reason. What are some other options? Why can't I see a single photon? I guess you guys don't really know what a photon is, so it's not fair to ask you this question, but who cares? Take a guess. Light is composed of photons in the same way that matter is composed of atoms. This kilogram mass, for instance, it has a mass of 1 kilogram, but it's made up of individual units called atoms. I can't see the individual atoms. Why not? In this case, it's because they're too small. But light doesn't work that way. It's not because the wavelength is too small.
Because they're moving too fast?
I agree that light travels very fast. At 3 times 10 to the 8 meters per second, it's the fastest speed allowable in nature. Then again, all light travels at 3 times 10 to the 8 meters per second. So if light was too fast to see, then we wouldn't see any light. That doesn't make any sense.
Because the human vision only can see so much.
Wait, but the human vision can see the color orange, correct?
Yeah.
Then you are capable of detecting 600 nanometer photons. So it's not outside the visible range or something like that.
I'm just spitballing here. I don't know.
It has to do with how you detect light, right? Like these electromagnetic waves come in and they stimulate your retina, and your retina converts the energy of the photon into a chemical, into an electrochemical signal on your eyeball's retina. Let's see if we can find a diagram of the eye.
Eyeball.
So the light comes into the little gooey lens, okay? Let's draw on this. Here, let's make it orange. Here come your orange photons. Squiggle, 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 squiggle. And they hit the back wall of your eye called the retina, where the energy is converted into some kind of electrochemical potential. A little axon gets fired and your brain says, orange sherbet ice cream, my favorite. So you're converting the energy of the photon into an electrochemical signal. The problem is that a photon has an incredibly small amount of energy. So we could say that at an energy of 3.5 times 10 to the minus 19 joules, it's not about speed or fast or small. It's that the energy is too low for the eye to detect 1 photon. You probably need a minimum threshold of like 1 million photons before it triggers the senses in your eye. Kind of like how a mosquito cannot always be felt because they land so gently on your skin that they don't tickle your sensory receptors. Okay. That leaves us about 15 minutes before class starts. Sounds good to me, right?
Yo.
Little 15-minute break. Do us a world of good, I bet, huh? You guys should drink some coffee. I should drink some coffee. I'm really tired today. And there's no reason for it. No reason whatsoever. Okay, I'm going to take a little coffee break. I'll see you guys around noon, okay?
Okay.
Okay, folks, I am back. Oh, yeah. Okay. Hello. All right. Today we continue our lesson in the exploration of light, covering chapter 5 in our textbook. Let's grab our slideshow. Always helpful to have around. I'd like us to start talking about macroscopic view. Well, you know, maybe we should define what light is. That's probably the best thing to do. Okay, so here in slide 25, we can see a basic physics model of light. Sorry. Okay, so light, which we are going to explore today, is something called an electromagnetic wave. It's an electromagnetic wave. It has 1 part electric field and 1 part magnetic field. Let's take some notes on that. I'm going to try to bust out a new marker. This one's leaving much to be desired. So it has 1 part electric field and 1 part magnetic field. You guys will learn about the electric field and the magnetic field over time. The electric field is associated with static or non-moving charges, whereas the magnetic field is associated with moving charges. But fields are kind of like the essence of charginess that comes from your proton and your electron. Your probably greatest familiarity with the magnetic field is if you've ever taken 2 kitchen magnets and you've pushed them against each other so that you can feel that sort of repelling force that they have on each other. That's an example of the magnetic field. Now, where the moving charges are, we can discuss that later. But the electric field is similar to the magnetic field. Usually your experience with the electric field is if you pull socks out of a dryer and they crackle, or if you rub your feet on the carpet and touch a metal doorknob and get a zap. Those are examples of static charge in your everyday life. Light, of course, can be detected by human eyes only within a certain range of wavelengths. So we say that light, or beams of light, is comprised of small packets of light called photons. Photons have particle-like aspects and they have wave-like aspects. So what we tend to say is we try to consider them to be packets of light. That is, an analogy could be that photons are to light in the same respect that atoms are to matter. It's a pretty good analogy right there. Because light is a wave, light has properties that are common to all different types of waves. Let's look at a little animation to help us understand what's going on here. Although light has an electric field and a magnetic field, you'll notice the electric field and the magnetic field sit at a 90-degree angle to each other in space, and they kind of travel through space and undulate as they go. Here's a more sophisticated picture of light, showing you the electric field and the magnetic field as the wave travels through space. To get a better understanding of the relationship between a charge and light, I can show you guys these cute little physics Java apps here. S drive. And they have one on a radiating charge that I like. So here you can see a proton, and the proton is surrounded by an electric field. The electric field is not exactly light. It's kind of like the essence of charginess that surrounds your proton. The electric field tells other protons to repel and other electrons to attract. Now, in order to generate light, you have to make ripples or waves in this field. So if I take my proton with my finger and I give it a little wiggle, you guys can see little ripples or waves in the electric field. This is now light. Let's give the charge a little sinusoidal oscillation. Here you can see me adjusting the amplitude and the frequency. I'll make the frequency a bit higher. And you'll notice that as I wiggle this proton, a bunch of waves are rippling out along the electric field line. Okay, I'm going to erase this so I can talk about the properties of waves. Let's talk about some common properties of waves. And this is true for light, but also other types of waves like sound waves and water waves. They have properties called wavelength, which gets the symbol lambda in Greek. Wavelength is the physical distance that goes from crest to crest of your wave. So its units could be in meters. They could be in nanometers. 1 nanometer is a billionth of a meter. Or in some cases, we even tend to express them in a unit called microns or micrometers. 1 micrometer, that's the Greek letter mu, kind of looks like a U. 1 micrometer is a millionth of a meter. But the standard unit is the meter. So put a check mark next to that. Other properties of waves include frequency. Frequency gets the symbol curvy F, and it represents the number of cycles per second of your traveling wave. That's how many wiggles go by per second. Let's take a look at that animation of my electromagnetic wave again, and let's see if we can calculate the frequency just by watching it. So I'm going to imagine putting my marker, my cursor, which I think you can see, at some location right here, and I'm going to count as the crests go by. So we'll start at this, we'll start when this bump comes by here. So we'll start 1001, 1002, 1003, 1004. I get basically one wave passing by my marker every 4 seconds. So the frequency would be one wave, one cycle per 4 seconds, or 0.25 hertz. That's how frequency works. So frequency is measured in cycles per second, and the units are sometimes called hertz. A hertz is defined as a 1 divided by a second. Cycles are kind of a dummy unit, so you can say cycles per second even when you write it 1/seconds. Lastly, of course, we have energy. And you guys know the units of energy, right? What are the MKS units of energy?
Kilograms.
What the
Meters.
F? Kilograms are units of mass.
Oh, wait, MKS. The fuck?
You guys are making me want to split my wrists here.
Isn't it joules?
Joules. Okay. And joules are your MKS unit. However, joules are kind of like a big clumsy unit. And in the world of atoms, we sometimes want to use a tiny unit of energy. Introducing a tiny unit of energy, it's called the electron volt. 1 electron volt is 1.6 times 10 to the minus 19 joules. This is good for atoms. When you're trying to measure the internal energy of an atom, electron volts are the way to go. All waves have these properties. Waves have some traveling energy. There's a frequency, there's a wavelength. And of course, we can relate these things to each other. They're all intimately connected to each other. Here I go. May I erase? Any objections? We can relate the wavelength, the frequency, and the energy to one another. A single photon has a unique wavelength, frequency, and energy. And if you specify one, you specify all three. That's because they're connected to each other by these formulas or by these concepts. The speed of light is the wavelength times frequency, is a formula that we used in our office hours today, where c is the speed of light in a vacuum, 3 times 10 to the 8 meters per second. That's a constant of nature. I sometimes call that equation 1 because otherwise it's kind of awkward to say it. Equation number 2 is for the energy of a single photon. And that's E equals h times f, where h is a constant of nature called Planck's constant. And Planck's constant, h, has a value of approximately 7 times 10 to the minus 34 joules times seconds. I can also combine equation 1 and equation 2 into a third equation that I think is very helpful for students. It's also the energy of a single photon, but it's now expressed in terms of wavelength. For light, the meaning of this formula is that short wavelength is equal to high energy light. Long wavelengths equal low energy light. We practiced those equations in our office hours today, but we might do some more examples going forward. One of the first people who did experiments in light was Isaac Newton. And he used one of these bad boys here, a prism, to take white light and break it into its component wavelengths. I wonder if I have a light source bright enough to do this. Let's see if this works. Probably not, but oh. I actually got it to make a rainbow, but it might be a little bit dim for you guys to see it. You've got to get the angle just right. I used to love to do this demo in the class because I had a 400-watt light bulb. Actually, I wonder if I could. Whoa, this is a crazy idea. Can I break the light apart and get it to shine into the camera? That would be pretty tight.
What happens if you do it with your green laser?
Oh, okay, so if you do it with the green laser, it's really not interesting because the green laser is a single wavelength of light. This demo is really nice to do in class together because we're not going through the medium of a camera, which kind of distorts the colors. Also, in my apartment, I don't have a bright enough light source. This was almost bright enough to do it, but the angle is a little awkward. Also, the rainbow that I'm getting is very, very dim. I've tried to do it with a couple of different setups in my house, but it's not so great. The way the setup normally works is you have to collimate your beam of light. That means you've got to make the beam really, really narrow. Usually what you do is you send the beam of light through like a piece of cardboard with a thin slit so that your light ends up being a narrow, thin pencil beam. And when you strike the glass, white light is composed of a bunch of different colors, as you may have heard before. And the colors separate because of a property called refraction. Refraction causes purple light to travel slower than red light, and this kind of slows the passage of light through the glass. This causes a property called dispersion, which makes the white light separate into its component colors, and it creates a rainbow. The rainbow has a certain order to the colors. If you reverse it, it goes red, orange, yellow, green. This used to be blue in Isaac Newton's day. This is kind of like a cyan or a sky blue. They called this color, which we call dark blue, they called it indigo, right around 450 nanometers. I have a personal crusade to bring back the color indigo because it's a cool color. And then, of course, over here we have violet. Let's take a note about that. So if we consider white light, bad marker. Where's the good marker? No. Too many markers in my pockets. Okay, try this. White light can be broken apart separated, right, into a rainbow. And a rainbow is another word for what's called in astronomy the continuous spectrum. The order of the colors is always the same, and there's two directions. Sometimes people use the acronym for the order of the colors Roygbiv. Red, orange, yellow, I don't have a yellow marker, green, blue, indigo, and then violet. Now, this is the way people traditionally describe the order of the colors because it makes a cute little acronym, Roygbiv. Rainbows always have this sequence. I prefer the more colorful rearrangement of letters, so that I like to put violet on the left because it's the shortest wavelength. So I like to do VibGyor. That's my personal favorite. Violet, indigo, blue, green, yellow, orange, red. Some good numbers to remember. So there are, each color is associated with a unique wavelength. Wow, the purple looks really black in this CCD here. Red wavelengths of light are around 700 nanometers, where violet wavelengths of light are around 400 nanometers. So in other words, what your eyes perceive as color is the same thing as wavelength. This spectrum here is sometimes known as the visible spectrum because it's the wavelengths of light that your eyes are sensitive to. So we sometimes call it the visible continuous spectrum. And that's just another way of saying the rainbow. Isaac Newton was the first person to do this. He figured out that the beam of white light contains all of these colors, but I don't believe he knew how to measure the fact that the violet was at 400 nanometers and the red was at 700 nanometers. It took a while for people to be able to figure out how to measure those wavelengths of light. They had to use the wave-like properties of light. Of course, there are types of light beyond the visible spectrum, and astronomers are intimately familiar with many of these types of light because we use them in our everyday lives. Also, astronomical objects emit a variety of light at longer and shorter wavelengths than the visible spectrum. Let me take a moment to introduce to you a very important graph in this class. It's called the electromagnetic spectrum, and you can see it here in slide 63. Oops. So your eyes are sensitive to a pitifully narrow range of light from 400 nanometers to 700 nanometers. And technically speaking, that's actually a very, very narrow region of the complete electromagnetic spectrum. At longer wavelengths, we have the infrared regime. At very long wavelengths, light is broken apart into radio waves. At short wavelengths, we have violet, ultraviolet UV rays that give you a sunburn at the beach. At even shorter wavelengths, between 10 nanometers and 1/100th of a nanometer, light enters the X-ray regime. Those are usually produced in medical imaging and from nuclear reactions. And then there are very, very short wavelength gamma rays. These come from nuclear bombs and nuclear reactors. This is the kind of stuff that can turn you into a Teenage Mutant Ninja Turtle if you're not careful. All of this light is just light. What makes one type of light different from another is simply just the wavelength of light here, the distance from wiggle to wiggle. The problem is, as the wiggles get shorter and shorter, the nature of how light behaves becomes very different. This light over here is very high energy and can be very dangerous and can break apart atoms very easily. This is such an important graph that, sorry, let me clear my drawings here, that we should probably take this as a note. Okay. There's a concept called the electromagnetic spectrum. The electromagnetic spectrum is the totality of all the different types of light that exist in nature. We're going to represent the bands or the regimes of the electromagnetic spectrum with a little graph here. You can sort of think of this as being like the periodic table of the elements, except it's for light instead of for atoms. Having some focus issues here. So in the center, we'll put the visible regime. This is the visible. And this is your VIBGEOR. 700 nanometers on the right, 400 nanometers on the left. At longer wavelengths, we have the infrared regime. That goes up to about 1 millimeter or so. 1 millimeter is kind of like the rough cutoff from infrared into radio. Sort of over here, we have 1 micron. A micron is 1,000 nanometers, and a millimeter is 1,000 micrometers. So if you can imagine taking a millimeter and breaking it into 1,000 parts, that's what a micron is. And a micron itself can be broken into 1,000 nanometers. At very long wavelengths, we have radio photons, the radio waves. These are transmitted by radio towers, and even your cell phones broadcast light in the radio regime. At short wavelengths, we have UV, which stands for ultraviolet. Ultraviolet goes from 400 nanometers to about 10 nanometers. That's when it turns into X-rays. And at even shorter wavelengths, around 1/100th of a nanometer, you turn into what are called gamma rays. Gamma rays are the highest energy photons found in nature. They are super, super short wavelength, super high energy, and they're actually considered one of the 3 types of particle radiation discovered by Madame Curie, who did experiments with radium and polonium that ultimately cost her her life.
Isn't radium, isn't that like glow in the dark stuff?
No.
Or what am I thinking of?
Glow in the dark comes from a process called either fluorescence or phosphorescence. And that is sometimes by stimulating certain substances with ultraviolet light, you can cause it to re-glow in the visible domain. So glow in the dark ultimately has to be visible, otherwise your eyeballs wouldn't see it. Right, Brandon?
Yeah. I saw something online about these things called radium girls, where it was like they would paint this radium paint or something in watches. And they got really sick and stuff from it.
Oh, yes. So radium is an element in the periodic table that is unstable, or at least it has unstable isotopes. And they will emit gamma rays and X-rays. So
Yeah.
probably they were being irradiated with gamma rays and X. Okay, so there's 2 different senses of radiation. Unfortunately, the term radiation is a little bit loaded, and I usually get around to explaining this at some point in the class. If you're an astronomer, you use the proper term radiation to mean light. And that means all of this stuff up here. But if you're a doctor, or if you're a nuclear scientist or a medical technician, you might use the term radiation differently. You might use the term radiation to mean particle radiation. And particle radiation is the stuff that makes you sick. And it was first discovered by Madame Curie and broken into 3 different types: alpha particles, beta particles, and gamma rays. Now, what's confusing about this, Brandon, is that gamma rays are actually light as well. They're the gamma rays from this portion of the electromagnetic spectrum. But alpha particles are a helium nucleus, and beta particles are just a free electron. So what's messed up about the term radiation is if someone on the International Atomic Energy Commission is talking about radiation, they probably mean alpha, beta, gamma rays, of which only one is considered light. When astronomers talk about radiation, they mean electromagnetic waves, which are any of these.
Yeah.
You see what I'm saying, Brandon?
Yeah.
So it's a little bit messy because it's like using the same word to describe 2 slightly different things that are kind of interconnected at the same time. It's a whole effing mess. From now on, when I say radiation, you will assume that I mean light. If I want to talk about electrons and helium nuclei, I will say particle radiation. And we will be discussing both in this course. Okay, if I wanted to imagine what a single photon would look like, well, how do I want to do this? First of all, can I erase this stuff? It looks like some people are still writing, but I'm not sure. Michaela, you good? Thumbs up from Michaela. All right. I'm going to erase this stuff. I'll have to read that article about the radium girls. That sounds interesting.
Yeah, it's pretty kind of horrifying. But.
Yeah, I actually have a radioactive rock of uranium here in my apartment. I sometimes like to take it into my class to terrify the students. Maybe at some point I'll show that to you and bust out my Geiger counter, and I can scare you some more. Thank God you guys are now interacting with me remotely because I can no longer irradiate you in the classroom. Okay, so when we deal with light, we can deal with light in a macroscopic or a microscopic sense. So there are sort of 2 views of light that we need to consider. If we want to deal with the macroscopic world, that would be like here's a picture of dealing with the macroscopic world. I'll show you a picture or a little computer animation of a church, and you can see rays of light coming in the window. Now, we could call this a beam of light, or we could call the individual threads, we could call them rays of light. But even a single ray of light will contain billions upon billions of photons. You guys calculated in your office hours today that a bulb of light pumps out 3 × 10⁻20 photons in a single second. So when we talk about the macroscopic world of light, we might talk about a beam, or we might talk about a ray. And these contain, I'm trying to think of a word, kabillions might be a word that doesn't exist. There are names for 10 to the 20. Share screen. It depends how intense the ray is. Let's get that names of large numbers. So if we're dealing with 10 to the 20, there can be quintillions and sextillions of photons in a single beam of light. So let's say that they contain quintillions of photons. There's a $10 word. And then we might deal with like the microscopic world. The microscopic world is where we consider individual atoms. And then that's when we might want to talk about photons themselves. A photon could be thought of as a localized packet of light. It's like a little tiny wiggle that travels through space, but it has a wavelength and a frequency and an energy. These two things are related to each other, but it can be hard to keep track of quintillions of photons at a time. So we tend to either have two modes. We're trying to analyze light from a macroscopic perspective, or we're trying to analyze light from a microscopic perspective. I think there's a pretty good analogy here with temperature. If you guys remember the animated GIF I had for temperature, I had this picture where we imagined a bunch of atoms bopping around. If I wanted to talk about a single atom, I could talk about that single atom's kinetic energy. But once we're dealing with a big box of gas like we have inside of an oven, there's too many particles for us to measure their kinetic energies. So at that point, we measure a different quantity called, take it away, class. Kinetic energy of the atoms is represented by what physical property? The average kinetic energy of all these particles is called what? No? Nothing, huh?
Temperature?
Yes, thank you, Ian. That's the temperature. Temperature is a macroscopic measurement of the energy of the particles. Kinetic energies would be microscopic measures of the energy of the particles. It's hard to do both at the same time. Okay, let's talk about macroscopic views of light. Then we'll transition to microscopic views of light. I have things to say about both. Some macroscopic properties of light include the quantities luminosity and brightness. And these two things are what I'd like to talk about next. By the way, for the photons, we can usually talk about energy, wavelength, and frequency. That's a counterpoint. When I measure the properties of photons, I measure their energy, their wavelength, and their frequency. When I measure macroscopic views of light, I measure luminosity and brightness. So let's discuss these concepts. Here I go. Imagine that you could see photons coming out of a light bulb. You've got a light bulb and you turn it on, and once you send a current of electricity through it, individual photons, quintillions of them, begin to stream out of the bulb in all directions. Suppose you wanted to try to measure the energy of all of the photons coming out of this light bulb. There are actually tools that allow you to do this. Let me introduce you to one. It's something called an integrating sphere. Bet you never heard of this thing before. An integrating sphere has like a simple Edison socket, and you plug your light bulb. That's supposed to be a light bulb, but I didn't do a very good job there. Clear. Let's pick a yellow light bulb, okay? So here's your yellow light bulb. And you plug it into your Edison socket, and when you turn it on, rays of light begin streaming out in all directions. And then you kind of close over the sphere. The edge of the sphere is a photosensitive material, and Mr. Computer here reads out how much energy is coming out of the bulb. Of course, what you'd have to do is you'd have to plug in a fresh, brand new light bulb, and you'd have to turn on the switch, and light would constantly start streaming out of the bulb. And then you'd wait around, and you'd wait around, and you'd wait around. And I'd guess maybe you'd wait around until all of the energy came out, and that would be when the light bulb was dead. But that could take you months. And that means you start to realize that maybe you've asked the wrong question. Maybe it was wrong to start off by asking how much energy comes out of a light bulb, because energy is constantly coming out of a light bulb. Maybe instead you should have asked about the power or the luminosity. So these are concepts from physics. Power in physics is a measurement of energy flow. It's energy per unit time. And this is a measurement of energy flow. The units of power are the watt. 1 watt is defined as 1 joule per second. We saw that in our class today. Of course, anything that has energy in a unit of time can have a power associated with it. That includes hair dryers, guitar amplifiers. Hell, even your body has a power requirement. How many calories do we usually eat per day?
Can you just move for 1 second? Sorry. My bad.
Fine. How many calories per day does a human consume?
1,000.
What the fuck? Come on, guys. 1,000 calories?
Is it like 2,200?
Yeah, like 2,000 calories a day, 2,500. 1,000 calories would be like, I don't know. I don't even want to make a joke here because I don't know how it's going to go sideways. But 1,000 calories would not be enough for me to survive per day. I would be grumpy and hungry. You maybe could survive, but I think you'd lose weight unless you were completely sedentary. If you think about it, if you have to eat 2,500 calories per day to survive, that is, technically speaking, a power. It's just not a power measured in MKS units. It's measured in calories per day instead of watts or joules per second. A typical light bulb might have a power of 100 watts, right? That's the old-fashioned Edison light bulbs anyways. Now listen, there is another word that means the same thing as power. And that word for astronomers is called luminosity. We tend to use luminosity when we're talking about light. Luminosity is the power of light. So for instance, a light bulb like the one we discussed today could have a luminosity of 100 watts. Here's a key point about luminosity that we need to make. Luminosity is usually a fixed number or I don't want to say a fixed number because that sounds weird. Luminosity is a constant for a single object or for a unique object. And that means it does not depend upon distance. In other words, if I have a 100-watt light bulb, it doesn't matter if the light bulb is close to you or far away from you, it's still 100 watts. Here's another object that has a fixed luminosity. It's called the sun. The sun has a constant light output, kind of like a light bulb, but it's much larger than 100 watts. The luminosity of the sun has a fixed value of 4 times 10 to the 26 watts. One watt is 1 joule per second. Now, I'd like you guys to imagine, oh, by the way, here's another power consumption that I think is interesting. The annual US energy consumption this is the power of the United States is 1 times 10 to the 20 joules per year, roughly. There's a concept that's kind of cool in science fiction. Science fiction writers sometimes imagine, oh, I'm going to get that fly. Oh, I got him. But I smushed his ass all over the floor. Oh, that was gross. Hold on a second. There's a fly that's been bugging me, and he made the mistake of landing right near my damn shoe. Oh, that's yucky. Oh, okay. Now that carnage is done with. I'd like you guys to imagine that a futuristic society of humans, or maybe some advanced alien species, would be capable of creating a machine called a Dyson Sphere. Imagine if you could create a giant solar panel in the form of a sphere that completely covered the sun. And then, like some kind of a cosmic tick, you could just suck up all the photons coming off the sun in every direction. And you could power the energy of the entire planet for infinity. This concept is known as a Dyson Sphere. And it's kind of a cool idea that one day we might be able to cover the entire sun with a solar panel and just slurp up all of its energy. Suppose you could do that. Class, the question I want you to try to figure out is this question. How much energy does the sun emit? In 1 second. So if you could capture all the photons coming off the sun, how much energy would you have? Could someone answer that question for me? Michaela, I volunteer you. I think Michaela should answer this question. She's dying to participate.
I don't know, would it be the luminosity?
But how you phrase this is important to me. I want to know the energy. I ain't saying you're wrong. I'm just saying you got to get it right.
Okay, so wouldn't it be 4 times 10 to the 26?
4 times 10 to the 26 what?
Would it be joules?
That's right. Michaela understands that watts are a unit of power. So if the sun emits 4 times 10 to the 26 joules per second, then in 1 second, the energy produced would be 4 times 10 to the 26 joules. Michaela, is that more or less than the USA uses in an entire year?
It's more. Oh wait,
How many times more?
Well, it'd be 4 times 10 to the 6.
So in other words, 1 second of total sunlight could power the USA for how long? Let's do her calculation again. 4 times 10 to the 26 joules over 1 times 10 to the 20 joules per year. And Michaela correctly did that in her head. I wanted to make sure you guys can follow her. 4 divided by 1 gives you 4. 26 minus 20 gives you 6 years. How many years is that in plain English?
4 billion.
Say that? You're quiet.
Wait, it's million years. Not
Thank you. 4 million years. If you ask me, that's pretty freaking epic, right? Let's look at a fun picture here. Kind of a cool image from NOAA. Check out this cool picture. Here's the entire United States seen at night. Could you imagine that 1 second of sunlight, if you captured all the light being emitted in all directions, could power all of this for 4 million years? No more electricity bills, free juice for 4 million years. All the toasters and the Nintendo Switches and the street lamps, all of it. 4 million years. That's pretty dope. Why haven't we done that yet?
Because the sun's expanding.
No, it actually has a relative. The sun will expand 5 billion years from now, but right now the sun has a fixed radius. Consider this, Brandon. You can see the sun as a disk on the sky. If the sun was expanding, your eyes would see it.
True.
Try again. Why don't I capture all of those photons?
We don't have the technology.
Well, we have solar panels. We have integrating spheres, right? Is it that we don't have the technology, or?
Political reasons.
We don't have the will to have free electricity. I mean, I guess you would need something capable of covering the sun. I don't think our planet has that, right? I guess you'd really need a thin sheet. The bigger reason, guys, the thing that I was hoping you'd say is that we don't capture most of those photons. Most of those rays of light just travel outwards in a direction other than Earth so that aliens can see our sun as a little twinkling light on their sky. Most of those photons are just wasted and travel into outer space. There's only a small number of them that can actually make it to Earth. And those are the ones that are kind of pointed in Earth's direction, right? This is kind of an important concept. When I talk about luminosity, I'm talking about the light output in all directions. But when I want to talk about the amount of light that comes to me, I'm talking about a small fraction of that luminosity. And that's a different concept. That's called the brightness. The brightness is how much light you gather at your detector. And here's a good picture of how to understand it. This bulb is emitting light in all directions, but I can imagine a small cone of light which is captured by my eye or by a solar panel or by a camera or something. And this is called the brightness. Let's contrast the two. You capture a small amount of luminosity at your detector. And this concept is called the brightness. Brightness is defined as the luminosity per unit area, where the area is the area of some kind of a detector. So if you have a light bulb, and the light bulb is shining out a little beam, the brightness is kind of like how much light is coming through some small square area. Okay? And the units of brightness are watts per meter squared in the MKS system. Now, typically what you want to do is you want to imagine that the luminosity is being spread over a spherical shell. So here we focused on a single narrow beam, but what if I tried to analyze the entire surface at once? In other words, let's imagine I've got a star, and the 4 times 10 to the 26 watts just keeps getting spread out over bigger and bigger areas of a sphere. In that case, we can create a really famous formula called the inverse square law. So for instance, if the light is being spread over a sphere of radius r, I can calculate the brightness coming through 1 square meter panel by knowing that the surface area of a sphere from geometry is 4 pi r squared. And if I plug this into my area, I get a legendary formula in astronomy called the inverse square law. The brightness is the luminosity over 4 pi times the radius squared. That's version 1. Version 2 is where instead of thinking about it as the radius of a sphere, you think about it as the distance between you and the light source. And then its brightness is equal to luminosity over 4 pi d squared. It can be tricky for new students to know when to use version 1 and when to use version 2. We'll try a little sample problem to help you understand. They're both the same thing. They're both the inverse square law. I'm going to erase. Let's do a sample problem. Here's a sample question. Find the brightness of the sun at Earth at a distance of 1 AU. In other words, there's 2 ways to think about this problem. We could imagine that we're sitting here at 1 astronomical unit. Imagine that you're an astronaut on a spacewalk, and you're standing outside the atmosphere of Earth. So here's a picture of an astronaut stepping out of the International Space Station. They would be roughly 1 AU from the sun. And let's imagine that the astronaut is kind of like holding up a solar panel. This isn't a solar panel, but we can imagine that they're kind of holding up a solar panel and they're pointing it directly towards the sun, 1 astronomical unit away. Now, a square meter is actually kind of big, class. Much bigger than a pizza box. I've got 2 meter sticks here and I can barely fit them in the frame. You'll notice that my dry erase board, if I move back a smidge, Sorry. My dry erase board is pretty darn close to a square meter. So this dry erase board, which is almost as tall as me, is about a square meter in surface area. So class, we're going to use the inverse square law to solve this problem. We're going to need to know that the sun is 1 astronomical unit away, and the luminosity of the sun is 4 times 10 to the 26 watts. Which version of the small angle formula do you think is the best to use here? Version 1 or version 2?
Would it be version 2?
Yeah, because we want to think of ourselves as being some distance away from the sun. In reality, it doesn't really matter as long as you put the right things in, but I like to think of it as version 2. And we're going to put in the luminosity of the sun. Obviously, that's already in watts. What units should I have the distance in?
AU.
That would give me watts per AU squared. I don't think that's the right unit of brightness that I want. Any other ideas? I give up. I'm stumped. I can't handle this. This is too hard. I'm going to quit right now.
Can you repeat that question real quick?
I just want to know what I should put in for D.
Would it be meters?
Good. How many meters is 1 AU equal to? How many kilometers is 1 AU equal to?
150 times 10 to the 6.
Kilometers. How many meters is that?
Wouldn't you just times it by 1,000?
Sure. So what does that give us? Well,
1.5 times 10 to the 11th.
or 150 times 10 to the 9. 150 billion meters, okay? That's what we're going to plug in for our distance. So the brightness of the sun at Earth will be 4 times 10 to the 26 watts over 4 times pi times 150 billion meters squared. Punch that up for me. I want to see if you guys can do this right.
Got 1,414.7.
Excellent. Can you round that to 2 sig figs for me, Megan?
I do, oh, would I do 1,400?
That's right. What are my units?
Hold on. Would it be watts divided by meters squared?
That's correct. 1,400 watts per square meter. This is a famous number in physics and engineering. It's known as the solar irradiance. The solar irradiance tells you how much energy a perfect solar panel pointed towards the sun could get above Earth's atmosphere. Anyone want to guess what it is by the time it makes it to the ground and passes through our atmosphere? The solar irradiance is from space. At the ground, it's been reduced to 400 watts per meter squared. So that's the best you could hope a solar panel to get. I think our solar panels currently are 50% efficient, the good ones. So you can really only harvest about 200 watts per square meter, which is still a decent amount of power. You could power a guitar amplifier with a single square meter solar panel. That means that you lose about 1,000 watts in our atmosphere just from absorption and reflection. That's one example of how we use the inverse square law. We're going to use this all the time to measure the amount of energy that a planet can get. Okay, the inverse square law is a very, very, very important formula in astronomy. One of our labs was supposed to be the inverse square law. It's a cute little lab that I wouldn't have minded doing today, but it's kind of buggy. So I'm going to move on to a different lab, one on spectroscopy instead. The next topic I'm going to jump into is on light and atoms. We're going to go back to talking about how photons are produced. Do you guys want to, should we start it, or do you want to take tea break early, a little bit early today? What are you guys feeling? No thoughts? I don't know.
How long does it take to start it?
Not long at all. Okay, we'll push on. We'll push on to 1:30, and then we'll stop tea break there. Okay, we'll just keep it normal. That's a good marker. Okay. That means I have time to kind of start this module, and I want to talk to you guys a little bit about how an individual photon is produced. It's going to be intimately related to our lab today. So I need to kind of shift gears and go back to the microscopic world with you. That topic is kind of complete here.
Are we going to have to print up our lab day to write on it, or can we do it on a piece of paper? Because I looked this morning for the lab, and it wasn't under the lab section, I don't think. I think it was just our last lab.
That's because I was lazy and didn't do it. But I did get it up just before class. But so I'm sharing my screen right now.
During break, I can print it up, so it's not a big deal.
Yeah, it should actually just be a single piece of paper. It's here. It says LAB6 spectroscopy.
Yeah.
If you open that up, you should just get a single piece of paper. And what we're going to do is we're going to look at the spectrum of a bunch of different elements, and we're just going to draw in colored lines. Though this lab would be kind of cool. Does anyone have crayons or colored pencils floating around? That will make this a lot better. I've got a nice set of colored pencils that I'm going to use. But if you have some colored pencils or some crayons, this will work great. If not, you might want to use a program like MS Paint and try to draw in the colors using your computer. That's another option. Dennis, do you have colored pencils around or crayons?
Yeah, I probably do somewhere, yeah.
Markers, anything that has color, even a pen with different colors. Okay,
Yep.
cool.
Yep,
But this
cool.
is just one page that we're going to do today. It's pretty simple.
All right, awesome.
All right, so let's talk about the process of emission, which is basically what we are going to. This is how light is produced, and this is what we are going to look at in our labs today. So let's ask the question, how are photons created? The answer is by a process called emission. Emission is a process where an atom creates a unique photon of light. So for instance, let's consider a hydrogen atom. Class, what does a hydrogen atom look like? How many protons, neutrons, and electrons are in a simple hydrogen atom? Like say protium.
Isn't it one?
One what?
One proton?
And one electron, if it's neutral.
Yeah.
So in this hydrogen atom, I'm going to have one proton, but I'm not going to find the electron in the lowest orbit. So the electron can orbit at a variety of different distances from your atom. And this is something maybe I forgot to tell you guys last time. I don't know if it got lost in the weeds because that was kind of right in between lectures. But here are the potential orbits an electron can have. Electrons are not allowed to orbit the atom at any particular distance. It's not like the way gravity works. Atoms are held by electromagnetism. The electron can orbit here in this particular orbit. This is the default orbit called the ground state. It can also orbit here at a second orbit called the first excited state, or at a third orbit, or even a fourth orbit. But there are regions like in here and in here, there are regions where the electron is not allowed to orbit. And that's because the world of atoms is so tiny that you're kind of getting down to the fundamental resolution of space itself. Space is not smooth and continuous at very tiny scales. Space is instead discrete and choppy. Things can exist here, they can exist here, but they can't exist in between. One way people say this sometimes is they say that the orbits of electrons are quantized. Here's an orbit, the n equals 1 state. Here's another orbit, the n equals 2 state. Here's a third orbit, the n equals 3 state. And there are other orbits beyond these ones as well. So we would say that atoms are held together by a new force of electromagnetism, not by gravity. And electromagnetism has to do with charges. And we also would say that the orbits of the electrons are, let's come up with some fancy words. The orbits of electrons are quantized. That's another way of saying like pixelated or discrete. Or if we want to be really loose about it, we could say they're choppy, okay? Those are all different ways of describing the orbits of electrons. They're pixelated, they're quantized, they're discrete, they're choppy. They can exist here and here and here and here. Now, sometimes we find electrons not in the lowest energy state, but we happen to find an electron up here in what's called the n equals 3 orbit, or the third excited state. And the electron gets excited, it jumps up to this orbit, and it tends to orbit around for about 10 to the minus 8 seconds or so. During that time, 10 to the minus 8 seconds doesn't sound like a lot to you, but the electron might go around the proton 50,000 times or more. After that, the electron tends to get tired and it tends to drop. from a high orbit to a low orbit. And when it does so, it releases an energy in the form of a single photon. And this single photon is called an emission line. An emission line is basically a photon that has a unique wavelength, frequency, and energy. You can think of a laser as being kind of like an emission line, because there are atoms in this laser which are emitting a green light at exactly 532 nanometers. One of the rules for emission lines, or this is basically where all light comes from. Light comes from, so here's something we could say. Photons are produced when electrons drop from high to low orbit in the atoms. And these electrons are going to lose potential energy, and the energy of the drop is exactly equal to the energy of the photon. Let's write that down. The change in energy, the difference between the high orbit and the energy of the low orbit, is exactly equal to the energy of the photon that is produced. And for individual atoms, we can actually measure their energy states. Here, I think a couple of diagrams would be helpful. So here's the concept. I've got an electron. It drops from a high orbit to a low orbit. It emits a packet of energy in the form of a photon. And the energy of the photon is equal to the difference in energy between the high orbit and the low orbit. This shows you an energy level diagram showing you the potential energy of the electron at various states of an atom. When the electron sits down here at the ground state, that's the lowest possible orbit it can have. So we say that it has an energy of 0 electron volts because it's at the ground state, or the lowest energy state. Now, if something kicks my electron up to the next orbit, it requires exactly 10.2 electron volts to get up there. To go from the ground state up to the third state, you require 12.1 electron volts, and so forth and so on. Class, what if an electron drops from orbit 3 down to orbit 2? How many electron volts is it going to lose? From here to here.
1.9.
Say that again?
1.9.
Yeah, 1.9 electron volts. It's the difference. And that's the photon that we're going to consider here today. In fact, because I want to do something a little more precise than average, I want you guys to follow along with me here. Let me keep an eye on the time. Okay, we got this. Let us consider something called the 3-to-2 transition of hydrogen. The 3-to-2